odd numbers, at least 3 people. Yeah. So join. So we have how many groups? 3. Others who come to join the already existing groups. Now, as you look at machine learning models, kindly allow me to summarize the procedure for those models.
So we can do earlier.
This is the procedure. As you know, we have already split the data set into training and test set. So what I want you to do, I want you to train the model using train set. We are calling it train set in our coding. So once you train the model, you validate the model, that is testing the model. Testing the model. This is by doing the prediction. We do the prediction using the test set. We are doing prediction using the test set. Then after testing or validating, the third step is evaluation of the model. Evaluation of the model. So you do evaluation of the model. Then step number 4, I want you to show the relative importance of the features in the model. Relative importance of features. In the model. So if there could be any other challenge, I'm there, will be working out to support where there is any problem. So you are set to go and let us know how you are progressing. Victor, you are in this group. Dennis, head of this group. Where is Bennett? You in charge of that group? Okay. There is somebody else? Somebody else, eh? Oh, Dr. Edna is in charge of the other group. Eh? So those who will be joining us, will ask them to join the already existing group. Kindly make sure you have run something. We have 1.5 hours, up to around 10, then from there you go to another session. So if you have more, for example, if you are doing with the models, there is a Google documents which I sent to your email. You can practice the challenges. There are 4 challenges that I gave you through the Google form. If you manage to do them, you can also post the results, and I'll be able to see what you are doing in terms of the solution to the challenge that I've given you. Is that okay? Okay. So you are free to start the discussions.
Downloading from yes, how are you? I'm fine. Yes.
Kuna plus mbili. Mpaka hiyo comment ya nukta.
Mpaka tumefika hapo.
Malaria ini seperti hari
Ne operating characteristics.
I wanted to go to that and take care of what you wanted in the yeah, because time so we can train cannot change working
The first one is what matters. TikTok ni train tests, evaluate the model, and check the relative importance. What we were doing yesterday, but now we ongezea different other machines. Kama decision trees, simple machines, networks, then you remember the HTML document? So you open that, it's called inaitwa TTMS 2024.html. Have you seen it?
Hiyo nini tuko nayo.
Hebu fungua Art Studio. Have you opened a new one?
No. So this is just the one that we had
Yesterday. I think it's better if you start from a new page. You start afresh, everything afresh. Just close that.
close now.
Close. Close zote hiyo. Close tu zote. Close zote start afresh. Hata hiyo untitled closed. Okay, let's start afresh. Go to file. Okay, you can open that. What is your... Where are you from? Kama unaweza niondolea. Nifungeshe. Umefungua hiyo nini? Files zako zilikuwa kwa kifadha.
Excuse me.
Nataka nisongeshe nisimame hapa. Kuna kakebo hapa kidogo. Unafungua a new one, or you open the listing?
So you want me to open a new one?
Just open a new one. Just open a new one. So go to file. huko juu. New, file, and then choose add markdown. So give it a name, probably ya leo tunataka kufanya machine learning. Usiite jina, ita kitu yenye tunataka kufanya kama machine learning. Tutafanya random forest peke yake. Andika machine learning. Weka tu machine learning. Use current date. Change all those data. Then weka okay.
Maybe yesterday when I was playing with them,
So now that's one area. I think so now
Upwards or downwards?
Now we need to, first of all, before you run machine learning, you need to check the data. You need to come up upload data and so what you're going to do, we'll first load the wachana na hiyo, go back to that. So now set the working directory and this is the
I need to put I want you to run each for that.
so copy this, open a new chunk. So that's now working directly. So now open another chunk so that we will import library Tanzania. So these are so copies of libraries. So let's see if our libraries are installed. So they are there. Let's put another chunk here. Just go back to the other and now load the data. I'm not sure. I think we can still use the same data.
now to add the read CSV.
And you can also check.
It's like it's bike. I replaced Malaria. Oh, it has to communicate with directly.
So you can even use this one. Ziko features nyingi. The other thing, you can check, you can basically check the columns up.
Now here you put another inside. Not standards work. So that is not defined in the directory.
So, meaning the total number of your data set is 3,200. And these are the rows. And now the features are 14 features. Let's proceed to there was something that was commented. Just open the HTML, copy out what that is commented. Then remove the basically checking just check that. So for instance, the first one is the same as what you had previously. Check the features and then the summary of the data. So then you can now move to the next one. Yes.
I may not put as many as and we see that background if you are done. To hire you as
once you put a color, it will change to, you can see when you put green, it changes to green. So you don't put something like green. Alternatively, you can also put numbers. I think any number between 1 to 250. I think 0 to 250. So you can put without quotes, number without quotes. So you can put something. Umetoa tu.
So it's the work.
It's from 0 to 255.
Yeah. Visualization, it will you don't need to. So if you want
Yes, you couldn't get it there.
Green. So you can play around with the numbers to know the color. 0, 0, 1, I think ni so these ones we're using plots. To do the same thing. It has also many colors. You can put any color. You can put the numbers or you can put a specific color.
We needed that.
Black and white. You understand the data? These are the total numbers. saying the data set is highly balanced. Scatter is something different. You can't use scatter here. You can't use scatter here. This one is for checking the total number of negative cases and the total number of cases. That one is non-zero variance. Probably, I think you analyze to check if there are some features that are not very useful for a. So you can see the last one. So you need now to eliminate an important feature. Create another chunk. Now remove this one.
This there, whatever this part is Doc, I'm in trouble.
Yeah. Yeah, now remove non-zero. You see now we had 14 features. Huh? We now have 13. You remember what? Yes.
Rows remains the same.
Rows remains the same. Just the column.
And the column. This is the column.
Non-zero value. Ile yenye ilikuwa false. Ile yenye ilikuwa true. Sorry. Yeah. So you were saying, so long as you can change 3 to 1 or something else or 1,000
in a number.
In a number.
Change.
Hatujaenda mbali daktari.
I didn't download the things you said you downloaded.
You already have them. Now partition the data. Sasa pale.
The last thing. What's the name?
Now, you can see our data is partitioned into 70 and so you can change. I was saying you can change to 80, 20. 80, 20 is a good practice, or you can even do 90, 90, 20. 90, 10. But a good practice is training data should always be more. So run that to see how many training data you have. Go to the next quarter. Go to the next one. I think it should give you the statistics of the training. So you do the dimensions of training and the dimensions of and then you compare with see, we have records that we're going to use for training is 2,655. You can check against the 7030 kwa that HTML. Kwa that HTML. Si alikuwa amefanya yetu ni 80 yake ilikuwa 70. Ukamsia unaona yake ni 2. Sasa angalia test yako pia sasa. So these are the number of testing. 655. So once you build the model using the training, test using this one.
26. This is 8. 80%
It's actually not very big. 2,625.
Compared to 655.
It's expected that training data should be more. The number of hours that you use for teaching is more than the ones for exam. Am I training at least? You train for 7 years to go run for 9 minutes, 9 seconds.
So we need now the modeling information.
Yes. Yes. Model information now. Try comment here. Next, try your comment. So now these are our models. I believe, I don't know whether you have practices of machine learning models. Unajua mambo za that decision trees, different algorithms are decision trees. And even Choice, I think will depend on the data. For us, so angalia yenye ametumia, so inategemea na data.
Malaria, now I'm understanding what it is we assign.
There's something I want you to
It's radio. So I think you can consider
You also progress?
Yeah, tunaendelea mzuri. VM.
But you know we've changed that. We've changed the training data from 70 to 80. So I don't know, probably, but
imefanya 48 seconds.
Meran.
I want you to learn more on up to round 900. Number 100. Then you go to parts of pick the one best. Then now you have some just go from like to learn from them.
Probably we can just take maybe come and support vector, look at all the support vectors.
Let's go down, that's the support vector. Unaweza kutumia hiyo. Then you just run, then you run down to the base model of the 8 models. Because there are many.
There are many. Created a new one.
There's something else I sent you.
Yes, sir.
The way it is, copy
The command is still ready for information.
How can pass information to arena or research. Now this is what data and this is the model. Which is normal. You don't have a model that's 100%. There was no agreement meaning for data
And these are based on the test data that we have divided our data into two. So these ones are based on test.
this one is test data, this is one for the model. And from there, so we have seen that model. Now we see it down, followed by the region where you come from. You come from you have high chance of being tested positive for malaria. You come from here, for malaria is your thing. If you come from Nyanza, yeah, you come from Nyanza with that. How can you say they are making every use of our facilities and our partners, including the county, Makerere County, Masaraka County, Mary County, all those counties, you don't experience the same risk. So you can be able to see the contribution of people to value for that particular it's part of the list of the models that we take. So, still on the same. Minimize false positives. Usiseme mtu ako na ugonjwa na ana. It's a legal issue. To bring legal issue. We are been out to pay them money for misleading the institution. You must reduce on cost. On false positives. False positive zero. False positive zero. Even not possible, kuweka moja in 1,000. Kwa hiyo itakuwa side effect, but not killing. Even the use people to drawn automatically from the market.
Side effect ikiwa kubwa sana.
Even say hiyo dawa ipatia 100 moja mwe mmoja kama kitu kama 10,000 moja au kuna saidi kuona ni watu lakini huwa
Money training, our training doesn't 20.
ulifanya makosa ulipatia nini ulipatia mzigo
Tumeiran na ile the original, so it's 70-30. Inategemea pia na machine. Inategemea na machine.
unaelewa kama
Results za nini? I don't think tuliangalia results. The first one. Kina confusion matrix. The confusion matrix.
You should be winding up your activities because we want to move on to something else.
So where?
hii yake inafaa kuwa ingine sasa.
Tunaweza sasa, mnaweza endelea mkimaliza random forest. But he will that.
But this one,
So inamaanisha for balance, for nini, for imbalance positive ziko kidogo.
293. And this is controlled by the
So probably not one is not one. The kitchen importance is based on the model. So you can try the other. Which one is that? Oh, the rock house.
Yes. We are being no.
It's almost one. Yes, this one is position. The other one was round of forest. Yes.
Kuja tukaangalia for 10 minutes, tutakuta itafika around 10 minutes. So tutakuwa tunafanya tukute kila
You're in chemistry. This also
Sorry?
you also require that you understand the
You have to understand the data. Yes. Not necessarily the disease, but the data. You have to understand your data. But basically, as you do those visualization of the data, it helps you to understand the kind of data that you have before you build the model.
Okay.
If it is not there, we stop. Then it will proceed. What it takes time. By the time it's okay, kuja tunakuta alarm. Then check where there is sampling. That's the sample. Around line number 9.6. Around 9.6. Take from it. That is alarm. That's all I get it. So that you get one result at once. Attention please. We can go for a cup of tea, but make sure you are the first 10 models. Your script is training the first 10 models, so that when we come back, we see the result. It will take about 20 minutes, or thereabout, depending on the number of videos. So you are welcome for a cup of tea. I don't know, let's go ask. For a cup of tea.
Our Heavenly Father, we worship and bless your holy name. We thank you for the gift of life and things that are donated unto us. Among them, you have given us a cup of tea and a contentment. We pray that God will give you full nourishment of body, soul, Lord. Bless it and sanctify it with your fire. Provide it to them that do not have. For this is our prayer of faith in Jesus' name. Amen.
kuwa nazo but vile vile tunaitoa kwa kwa chini. Mwanzo tunaweza It's 2 minutes. It's 2 minutes. Takuletea tu a small online form for you to fill in your details. And then you submit. When you submit, that email will go to and then after every training like this, when I suspect I
Okay, members, we are going to keep Professor Molini. Karibuni. After the swallow, we will give Professor Molini 20 minutes to wind up so that at exactly 11, we change over to Dr. Okongo.
Me too, I'm in chemistry. That's what I said yesterday. But think about your you are closer to malaria than all of us here. Easy
Hello? I want that we conclude on machine learning, and I hope you are able to get the results. That I guide you on how to normally do comparisons of the models. Did you? Are you able to? Do you have the results? Check on your machine. Then still learning, or you have the results? Now, I know in your groups there is a laptop that has the final results, so that has completed learning the results. So let's use the laptop that has results similar to what I'm displaying there. You okay? It is still working, eh? So don't interrupt. If it is still working, don't interrupt. Because we need to get the results. So give me attention so that I can make something here. Maybe 10, 15 minutes, and then that's why I told you, I think that data set that we are using is heavy. And that's why it's taking time. Now, are you able to see this result somewhere? We can zoom. Let me zoom.
You're saying so we should see the Mikimaliza brand.
Missing package.
It keeps on needing when it stumbles upon some soil.
Okay. So we have results for how many models? Around 9 models. These are the results. So for each of the models, these are machine learning algorithms or models. There are 10 of them. And we want to make a decision about which is the best model that we can use for malaria prediction. So if you look at the value for balance accuracy, I said we are using data that is imbalanced. The data is imbalanced, therefore is subject to biasness when making the model. So you look at which of the model has the highest balanced accuracy. So if you look at all this, which one has the highest what? Balanced accuracy? 9670? 9, where is it? The boost. This is the best model that you can adopt for predictions of malaria cases. So once we choose this, once we use this particular performance matrix, we'll be able to get the predictions that we want. What does it mean by having 96? It means 96% of the cases will be classified correctly. Either something is positive or negative. Even others, you cannot still consider them, but for this particular case, I want to narrow down to balance accuracy. Another way you can also compare and choose the best model is through, you can do a plot. Let me display the plot. So these are the models. Then the summary, but we also have the summary here. You can check the summary for each of the models. Yes, that's a summary of the 9 models that we are working with. For each of the model, you have the statistics, the mean, the first quartile, the median, the mean, the third quartile, and the maximum value. Then we also, this is on the accuracy, and then we have kappa. What is kappa in machine learning model? Kappa tries to show the agreement between the actual and the predicted values. So the more, the bigger the value, the more we say there is agreement between the predicted and the actual situation. So if you look at for the boosting, let's use the median. Take the median, look at the median. If you look at the same model, boosting, the kappa value is around 93, 94%, which is higher. We have also bagging, also has a good result. That means you can also choose to use a bagging model, which has also 98%. We also have S3 model, it has a mean of 93%. So, but all the, at the end of the day, that's either boosting or bagging is classified as one of the best models that you can use for malaria prediction. Now, why is boosting one of the best models? It's because boosting is an enabled model. It's called boosting. This model that fall under that particular model. And what happens when it's building a model, it tries to correct the error of the previous model. So anytime it is running, that's why it takes time, it tries to correct the error of the previous model. Remember, it's a set of complex models. So if there's an error that was made in the first model, it tries to correct until you end up with the best model from that particular algorithms. Then the accuracy is the same. You can see the value. We can also display this using plots. I want to show you how we narrow down to the best model. This is we can draw what we call box and whisker plots. I want to display this. Yes. This is the accuracy. This is what we call box and whisker plots. This value you see outside, this value that you see outside this box, it is an outlier in the data. And anytime there is an outlier, you see there will be a problem when you are training the model. So all these models, they have an outlier. Look at all this, they have an outlier. Then how do you correct that outlier? If there's an outlier in the data, before you training a model, this is where we do what we call pre-processing. You do the scaling and centering. If you look at the code that I gave you for machine learning, there is something that I've stopped from learning. Check on your account. Maybe you can check. Something that is written pre-processing in your code. That particular code, if you remove that hash, the code will learn and it will give you different results. The first model, SV model. Could you just check? Could you? Line number. I can check for you. Line number.
Line 177.
Around 177? Okay, mine is around 180. Within that particular training on support vector machine, pre-processing, scale and center. What do we mean by scaling?
Line support SV model.
Line, I think 172 or 178.
Pre-process.
170?
It's blocked.
It is blocked. So if you want to address the issue of outliers in the data set, you just make sure you have unblocked that particular line. And also there is tune reg. Can you see the tune reg?
Yes.
The tune reg. If you remove those two, hash, this is what we have. I'm trying to tune my model. Tuning is trying to, we call it hyperparameter tuning, try to optimize the performance of this model when you are training this model. So it will give you some good results that can tell you when the model performs well. This pre-processing, the scale and center. Scaling, you want the outlier to be very close to the center of the distribution, or to be very close to the majority of the observations in that particular data set or variable. Then the center, we do the center to normalize. You want to normalize the data so that if there is any issue with the way the data was captured, it is normalized in such a way that the model is able to process or to train, the model is able to train using the data that has not problem. So when you run this code, I want to run this code separately for training the model, if you allow me. Kindly. If I run this model, and then I plot the model to see at what point do we get the optimal results. So let's be plot the model. Once it runs, I know it takes time because right now it is trying to optimize the performance, try to do the scaling, the normalization for you to get the best model, for you to be able to train the best model. Once we are done with that, we'll be able to plot the results. So at the same time, there is what we call dot plots. Maybe I can display this. Oh, just results. We have the results. We have the results. So this is the result of the model that we are going to optimize. This is the accuracy of cross validation. Then you have the cost. The optimal value is obtained at this particular point. Very close to zero. So if you look at the result of that model, you will get the results, the best results at a point where the value of C is 4. This is 4. This is where you have the maximum value. This is what? This is 97.1. Any other value that is higher than that? No. So this is the current cost, but it is parameter of regularization. And therefore, at this particular point, you are able to get the best result. If you learn the general, the comparison section of the models, this model will not have the outlier the way we see in this particular graph. The outliers will not be there because I've already addressed what? Outliers when building this, when training this model. Let us. I don't know if I'll not be able to run, but because it will take time. This outlier value that you see, these outlier values that you see, I'll be able to address them when you tune them, when you do the pre-processing of the data. They all of them will disappear and will not appear in your lab. Now, the one with, we call it what? This is with a small box, shows it's the best model. And because it is the best model, the R is able to give you the model in order, in rank, we call it rank, the order of the best model. So this is the best model according to this data that we have used. You start with the random forest, then the bagging, the boosting, and this is the least model that you should consider for malaria prediction. Are you together? This is the least, don't choose this one. This is the best. But I'm telling you, the reason why you see this particular is because we have not processed the data. So when you are doing the comparison and you see these outliers, just reprocess the data and most of them will disappear. And then you'll be able to know which is the best model. We can also use the box plot. Box plot, I think it's there. The reason I'm not learning it is because it will take time. Especially the boosting, doing the corrections of those, it will normally correct the errors of the previous model, it will take time. Even this one, where we have the dots, can you see RF is still there? The best model in terms of the accuracy, and also in terms of the kappa. Kappa is a value between, says between -1 and 1, it's like correlation. So the higher, when it is very close to 1, the better. When it is close to 1, the better. Then even accuracy is a value between 0 and 1, because we are talking about 100%. We want a model that is, even if it's not 100%, but close to 100. So this is how we do the comparison and be able to choose the best model. These models have been ranked in the best of the most suitable model for this particular case. So if we have now to discuss and make a conclusion on which model do we recommend for malaria prediction or malaria diagnosis, we recommend the random forest. Are we together? Yes. So I think that's how we do the comparisons and make choice on the best model. Now, to correct the issue of the imbalance in the data, we do the sampling. We do the sampling, and this is how we do the sampling. For instance, if I'm handling this is what? This is undersampled data. I want to undersample the data. Undersampled, if we say if I have the minority are 150 and majority are 500, you do this from 500 to what? 150. How do you do it? There is this code. Create under, then we have this function, then the same target variable. The data is training, don't touch on the test data. The method you put under. If you want over, you put over in this particular part of the model. If you want hybrid, you write both under and over. It's just the same code. And then you run this particular data. When you run this, you end up with a new data. This is the data that I've undersampled. We try to balance the classes or the instances for you to be able to get the best model using the data. I gave an example of why we are doing this. If you have 20 students or 20 people, 15 on that corner and 5 on this corner, then somebody enters this room. And I ask him to join any of the group. Which group do you think they will join? The larger the group is the majority. Only there is biasness. So we want to remove that biasness by making sure instead of having 5 on this corner and 15 on that corner, we have 10. So there is equal chance of you being in any of the two groups. You can be in any of the groups. So we want the model to be in such a way that it is not influenced by majority cases. Are we together? So for undersampling, this method it is under. If it was oversampling, I don't know whether it is there. Yeah, it is there somewhere. Sorry. I think I was displaying the wrong results. Oh, these are the results for our models. Sorry for that. So let me finish with the sampling process. This is for the code for the over. I hope you can see it's the same function, over, then the function, and then what? The train data, then the method is over. I'm oversampling. moving from 150 to 500 because the largest category has 500. So I want them to be equal. So it will duplicate to ensure that we have equal instances for the two of them. If you want to check on that data, not that you can check on that data, we can check on this data. So allow me to run this briefly. So I need to run the operator for it to accept it. So we will not find this. I think because I need to run the order of that, it will not run. But once you have done oversampling, look at what happens. The test, the positive and negative are all what? They are all have equal instances. So when you are training the model on this kind of data, there will be no biases. You expect somebody to be placed in the right category. If you have malaria, you find yourself in that category with the malaria. If you are test negative, you find yourself in the category that has people with no what? Malaria. If it is for the other one, that one was oversampling. If you look at the other one, which is oversampling, I think it's the same. This one, this is under sampling. Look at how it is. So we say close to the minority. So it is trying to make sure that it is compressive. At least it is close to around 150. So although there's a small difference between the two columns, don't worry. The model will be able to address the small variation that is there. And finally, I don't know whether I have the results for both. We call it what? High print. If you look at this, I want to use the high print function or method. So you can see the code here. We are using what? Both. Now you must run the data under, over, and both. Reason B, you don't know which one gives you the best model. Then you compare the results when you have undersampled, oversampled, and hybrid. And then from there, you choose the best model. The good thing, all these things you can do in R. You just make a command and you get the result. So that when you are making the combination about the model that is going to be used, you are sure that it is the best model. Remember, we don't need to develop a model that can mislead people. If we may come up with a model and then people die because of our model, they will be taken to court and we plan to pay a lot of money. So you have to make sure you have taken into consideration all the assumptions and things that we need to consider before we come up with the best model. I think that's all. The only thing that I've seen is on the result that I was explaining today. This one. These are the best results. I think once you are punched as generated, this is the results it's generating. Yeah. So this, but it is still the same concept. These models are learned in from the best to the least suitable model for prediction. So in this case, you can see the boosting is the best. It has higher accuracy close to 1. But it is very close to 1, which is almost 100%. Sorry? It's almost 100%, although it's not 100, followed by random forest, and the padding is also there in that folder. Then, if you look at the kappa, again you can see the kappa. It's on this side. So it means there is a kind of agreement between actual and predicted values by the model. I think that's all. Thank you so much. Yes.
My concern is on sensitivity.
Sensitivity, yes.
When I look at all of them, they seem to be less than 7.
Less than 7.
The sensitivity is less than 0.7.
Let's check.
You can check any model.
Let's see. Oh, yes. Where is sensitivity? This one. This is 7. I think this is 7.
But there's one for 9.
There's one with 9?
Yes.
Okay. Let me zoom.
DG.
You can check on this. Let's check on this. Huh?
Yeah.
Which one?
LDA is 0.9.
0.9. LDA is 0.9. But when it comes to balance accuracy, it's what? 0.924. Do you have a model that has the highest?
So I believe my suggestion is that LCA was the best. Because the sensitivity, specificity, and accuracy.
Now, this is what we do. Even after doing the performance metrics, there's something we call ROC or AOC, area under the curve, where we try to show a graph of true positives and false positives. Our model should be able to minimize the true what? The true positive. So if this one is not able to give you the best result, we can also go ahead and try to interpret the result of the AOC. Can I check on the result of AOC and see which one has better result, so that we make a decision? This is not the only, this is one of the measures that you can use to judge on the model. But there is also another performance metric that we can consider. Let me check one. Because at 11 we should be starting on another session. For instance, this one. This is AOC. Look at the area under the curve for this particular model. This is the boosting model. This is false positive. We are reducing on this. Out of 10 people who, let's say, have malaria, those are positive cases. The model should be able to tell us almost 9, if not 10, almost 9 are true. It is a true situation on the ground. That's why you see this value is almost very close to 1, and then the false positive is very small. The whole of this area, if it is a square, let's put this is a straight line like that, the whole of this will be 0.1. No, 1.0, because it's an area as what? It's supposed to be, yeah, it's supposed to be 0.1. But can you see there's something here? There's a small area that is left to make it 1. So for the boosting, at an area of 0.99, so when I'm making the decision to choose the boosting, it's because this one confirms that the number of positive, true positives is higher and minimum false positives.
How is AUC for the LDA?
For?
LDA.
LDA. I don't know if you are able to draw. Let me check whether it is there. LDA. So this is L, PQ. Let me check. LDA, this is LDA. Can you see it is 0.98?
Yes, now, Prof,
yes.
It goes back to what he's saying. Being a malaria practitioner,
yeah.
I'm sure he's, in malaria practice, the 3 factors, specificity, sensitivity, and accuracy, are very important.
Yes.
So we have seen that LDA combines the 3 very well.
Yes.
And we are also seeing area under the curve. The LDA is still performing very well.
Yeah.
It is above 0.9. So why are we not picking on it and going for the boost?
I want to show you something, that the sensitivity, let me show you something on the same. If you look at my dissertation on those metrics, you allow me to check something here. Sorry. I have all the quotas in one. So let me quickly do this in my dissertation. What is true positive? Yeah? Let me check. Can you see true positive rate is sensitivity we are talking about? True, this is sensitivity of true positive rate. So when you are talking about true rate, true positive rates, you want higher, an increase in true positive rate in my R. This is the.
Can you zoom it?
I can zoom this in. Yes. Look at this. If you do a graph that compares the true positive rates and false positive rates, they have an area of 0.98 for error G. Then the boosting has 0.99. The one with the highest area under the curve is the best one. It means the positive rates is higher than false positive rates.
Prof, what we're asking is,
yes,
LCA has high sensitivity, high specificity,
yes,
and high accuracy.
Yes.
Boost has high specificity, high sensitivity, and very low accuracy.
Yes.
Why should we go for boost?
For boost.
And sacrifice on the accuracy?
That's what I was saying. Under the performance metrics, we don't add on the sensitivity, the specificity, and balance. We still go ahead and check on force on area under the curve to make the final decision. Remember, this combined takes care of the sensitivity we are talking about. What is the error? What is the false positive rate? Because we don't make decision only based on this is what? The specificity. Can you see this is what? Sensitivity, which takes into consideration the what? The true what? Where is the true what? The true negative rates. Then the balance accuracy is the average of the two of them. Can you see this balance accuracy is the average of sensitivity? Doctor, how? I'm responding to your question. Why are you narrowing down on this? This takes into consideration the average of the two measures. And then we confirm using area under the curve to make the final decision about the best model. Remember that one is okay? Somehow, the method want to come up with a model that will not mislead the public or will mislead the implementers.
Even without looking at the slides, we are saying there is a model.
Yes.
One that is very high on sensitivity.
Yes.
Very high on specificity. Very high on accuracy.
Yes.
Model B is very high on specificity, very high on specificity, very low on accuracy.
Yes.
We are now picking this one with low accuracy and leaving this alone.
When making decision, we consider all of them, including the area under the curve, to make the final decision. Victor, we have worked on this. You can learn something.
I wanted to add something on F1 score. Well, if you were to look at sensitivity and specificity alone, we might end up picking a model that's not doing really good. We have to look at other factors like F1 score. F1 score combines how good the model is doing in terms of sensitivity and specificity. If you look at that model, I don't think LDA is doing good in terms of F1 score. So we have to put into consideration all other metrics for us to pick the best model.
Is that okay?
That's it.
Yeah, all of them, they are not separated. You must take care of all the measures to make decision about the final decision. So I think any other question? Because I want us to move to the next session. Okay. Thank you, Dr.
So we want to thank Professor Moridi for that session. And I think this is the last one for him, isn't it? So we thank him for the work that he has done. Let us give him an applause. Five factorial mathematics, 5 factorial from Professor Moridi. So let us start. Malaria straight. We have to finish some to exercise so that we cross over to Congo. I will try, but I'm afraid I will fall. If I fall, it's going to be laughing.
Okay, we may start and stretch a bit so that we get ready for the next session. Get some space, get some space. Get some space. And we stretch a bit so that get some space, get some space. Okay, so we start by that. Then we go down. Alice. Okay. Go to the floor. Go to the floor. Okay. Baba. The other side. The other side. The other side. Let me go up first. Then we go down. Then we go down. Go down. Okay. 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 Oh man. Don't be like a tree. Okay, we go in front. We go in front and you touch what to. That's what I can try. Just touch what to and relax. Okay, and come up again. What we did yesterday. In front. Pull it. Then hold on. Okay, the other side. Pull it completely. Then on your shoulders and pull it. That's it. Okay.
Good morning. Still working. Now realize that yeah, I've realized that we needed to we included a lot, and we may not be able to adequately cover what we planned to do, but I'll try to see what we're able to do. Now we started from what we have done because that we thought is very important for everybody who came. So in modeling, we said that all models are wrong, but a few are useful. All models are wrong, but a few are useful. So how do you make your model useful? What makes a model useful? If you have a useful model and people have interacted with it, then it can be inbuilt in the R software so that people can use it. Right? So what makes a model useful? If the result of the model corresponds to the reality on the ground. On the ground, right? If it doesn't, then the model is useless. But you can make it useful by reworking on the model, right? Let me ask a question here. How many people here, if we have interacted, you have been able to run data on the SVM model, right? So let me see, how many people have interacted with the SVM algorithm? Remember what we are doing, there is an algorithm which we are defining as the models. How many people have interacted with the SVM algorithm? Professor, I know I did a lot on SVM. Before machine learning, just the SVM model, right? Somebody else, hey, how wonderful our statistics. Study the SVM algorithm. Can you write it for us here?
No, we use the 8
So that's why I want to take us to another level, because this is the university. I want to get this students of MSc and PhD. The university, we are interested to understand your contribution in academia, right? We have the SVM model. There is the algorithm for that model. Are you able to improve it so that it has a higher level of sensitivity, accuracy, right? Remember now what we're doing, you are given a data set, then you are testing that data set on different models, then you finally settle on one which will address the problem that you are handling, right? But so we can take it a step higher, and I'm not sure whether everybody will now can get that. We can take it a step higher, where now we want to check the algorithm, right, of that model. And now you want to improve on the algorithm so that we improve the model. And I'm sure that keeps on, that goes on. And that's why we have updates. I'm right. I believe, Prof, that's why we have updates on these models in R. The improvements on the models is what now brings the updates in R. So if you have an SVM model, maybe after 1 year, you'll find it updated. So what brings the updates? These are these improvements on the model. And for you to improve the model, it means you must understand the algorithm so that you work on the algorithm to make it better. Are you together? All models are wrong, but a few are useful. So let us start from there. I want to understand how maybe we can improve on a compartmental model which handles malaria, right? So for what we really do in applied is you may have some data, right? You develop a model, Then you have real data. Then you test your model based on the data that you have. Then see how your model behaves with that data. Then that might call for improving your model so that your model does not become useless. Are we together? But most of them are useless, are fairly useful. But in the business of making useful models which can be applied or which can be consumed. Now, I hope you managed to download the files I sent. And you can put them, if you put them in a folder, and even if you don't, but you download these libraries, then I want us to be there before we make some steps. You can start a new one, or you could just use the TTMMS. But so long as you open the file, DERMD, so long as you're able to open that in hard markdown. Let's go on the same page. I want everybody to be here. Just open file. Just open the file. Well, this file, which is the DERMD, yes. You are there. Can you run the packages? Yes. That one, have you downloaded it? Open. Okay, just so that
Did you manage to download?
So once you be, I want us to have these packages, so we'll be running our files. Able to run it. these two packages are very important. The diesel and the DIFA, this DIFA R, are very, very important for this particular work. So what does if you are there, then we move from there. It's not everything, but very important packages, libraries, is the dissolve, the DIFA, and also the DD plot for plotting. Now, I want us to, as you install the libraries and the packages, I want us to look at this. Now, if you look at this SIR equation, I was wondering, is there a disease that we can model by SIR? Which one? Chickenpox, right? What about common cold? So it may not be able to serve the purpose. Now, I want to start by saying this. When developing a model, first, you must understand that the phenomenon you are handling corresponds to which mathematical formula. Remember, a model is just another mathematical formula. So you must understand that which phenomenon, the phenomenon you are handling, it corresponds to which mathematical formula. Because if somebody asks you, like for this particular case, we're using ODEs, and then somebody will ask you that why are you using an ODE to model this disease? Remember what I said? Like those in academia should listen to this, because this can be a question we have to struggle with when you're defending your work. Why are you using ODE to model malaria? Why not simultaneous equations? And answer that question. Soon we want to see your thesis, and that might be the first question we'll be asking you. Because remember, academia should be able to produce knowledge, right, which is consumed by the public, right? Like remember the machine learning that we have been doing, we have consumed. But there's somebody who developed the model and was now able to put it into what? Once it's discovered that the model is useful, then now it is inbuilt in what? In R. So why are you using all these to model? Because we can use other methods, other mathematical equations. Why ODE? Because somebody so you don't just do a model, you must know that which this phenomenon of handling corresponds to which mathematical equation. If you have a phenomenon which, if you visualize, behaves like that, then from there you should be able to tell. You can have a variety of equations which you can use to model that kind of phenomenon. Then you finally settle on one, right? Because we're in malaria, I don't want to do that, but when we come to this one, when we'll be doing modeling, then those are where we'll be starting from. Now, I'm picking ODs for this particular case because we are modeling the rates of what? Rates of change. That's why I'm picking what? I'm using OD. I could have gone for PD, but will that give me rates of what? Of change. So as a modeler, any phenomenon that is happening, I should be able to develop a model for it, but you must have a good background in your mathematics, so you know that this one is stochastic, this one can be done by a deterministic model, and when do I maybe use what? ODE, when do I use a PDE, and ABCD. Those in academia again, remember we expect you to generate knowledge, not just to apply, not just to see. We want you to generate, so that we know that this model came from Teddy, and now we are now able to consume this model. Now, so we have this model. This is so the first model. This is inbuilt in R. You'll find this in R. The malaria models I have down there, if I'm not yet there, then from what we do here, you'll be able to go through it, is not in R, which means you write it yourself, you develop it, right? Then you code it into what? R. Then you run it. Then compare the result you are getting from the real data on the graph. That will inform whether you need to modify it or use it. To make it use further to be useless. Now we have this model here. Let me write it. Mathematically, this model behaves like this. This is an SIR model. ds dt equals to minus beta si. Then we have di dt equals to beta si minus gamma I. Then we have dr dt equals to gamma I. Now, I want us to move together. I'm saying that is inbuilt in R. You'll find in the R packages, right? Now, if you have to model a disease using this model, what are you assuming in this model? What assumptions are made in this model, obvious ones, which might make the model useless? Yeah? Yes?
Yeah, because when you say the DS, if I remember my math classes well, DSDT would mean the rate of change of those who are susceptible with the time. So you are assuming that the only factor of change there is time. But there would be other factors that would cause a change in...
the other factors that would have changed, cause a change in S. So when you are looking at a change of S with respect to time, change of infections with respect to time, change of recoveries with respect to time. But is time the only factor that would affect S, I, and R? Okay, let me start from somewhere. I'm assuming some things. Those who are with at Kipri, at least you understood how you are able to bring this one. Now remember,